Discussing the many examples on continuity equation and its application, now we consider another a very important consequence, a very important corollary of a continuity equation which we use in our fluid flow, and we define a function what we call as a stream function. Stream function represents the stream that is moving in a fluid flow, and first we consider it in Cartesian coordinates. We know that the continuity equation in 2 dimensions is written as, let us say, divergence of V equal to 0 by du by dx plus dv by dy. So we start from the simple version and then we move on to a more difficult thing. But from here, we define a very important factor which we very widely use in all discussions of our fluid flow, and to describe the fluid flow in many of its manifestations. It has a lot of utility, as you will see when solving many problems and when considering many problems of the fluid flow. We try to form, what happens is that when we are considering this equation, we are taking different components, u, v, w, or in 2 dimensions u and v. So there are 2 functions, u and v. A very clever idea to define a function that is one, that combines these 2 into one, is defined. And first of all, it was used by an Italian scientist, researcher. Anyway, it's very useful for, and it's very commonly used now. We define a function what we call as psi, and this is a stream function representing the stream, such that q is equal to d psi by dy and v component is equal to d psi by dx. When we substitute the value of u and the value of v in this equation, in the continuity equation, you can see that it is identically satisfied. And by doing so, we obtain this equation. When we substitute these values for u and v as defined earlier, we obtain this, and this is equal to 0. And in fact, it does not really matter whether we first differentiate psi with respect to x or with respect to y. That is not quite relevant. The important thing is that the second derivative of psi with respect to x and y, it satisfies the condition. So psi is equal to some function depending on x and y in 2-dimensional motion. That is the important thing. And therefore, the clever thing, the advantage here is that we have reduced 2 functions into one, and now if we have to determine the motion by finding out u and v, we have to find out 2 unknowns. Here, if we can determine only psi, we have determined the fluid flow. Because from psi, we can find out the value of u and v. And therefore, the order can be changed and it does not really matter. And therefore, the equation is identically satisfied. There can be other definitions also for psi, but the one that we have written here is most commonly used. In different coordinates, x and y, they are written here. This is rectangular coordinates. This is cylindrical coordinates, r theta. This is axis symmetric cylindrical coordinates. And this one is again if the fluid is incompressible. The last equation is when it is compressible, and that is why rho occurring here, but the others are incompressible. All other formats are for incompressible. So these terms are widely used in solving problems of fluid flow. And different stream functions, their graphs are shown here. for different values, they look like in the form as we have been shown, and they actually represent the flow, the fluid that is moving across. And this is similarly for a arc length, and while this one is in the form of a rectangular coordinates. And then we see that along a streamline, and this is again taken from the earlier equation that we have written, you can see that V is equal to d psi by dx, and the continuity equation is satisfied here. So along a streamline, we have these values, and these are different forms of the same equation. If V is replaced by d psi by dx, we obtain this equation. The total change of psi, this can be written as in the derivative form, that d of psi is equal to as partial derivative of psi, then dx, partial derivative of y, then dy, and this is equal to 0. If this is equal to 0 and we integrate it, so what we are saying is that d of psi is equal to 0. If I integrate it, I am saying that psi is equal to constant. So another important conclusion, that psi, the function psi, as described by us, as it satisfies the continuity equation in the way that we have described, it is constant along any streamline. It's important to qualify this statement that psi is a constant, it is always a constant along a streamline.